All right, good afternoon, everyone. Let's get started. Welcome to lecture 8. And I'm looking at the chat. There seems to be, is there a problem with the panelists? So you folks who were selected to be panelists for today, you're not co-hosts, is that right? Okay, so let me take care of that then. And we have 5 panelists today, so it will take me a little while to do that, but let me do that. I don't see our first panelist. I don't think they joined. Our second panelist, and I'm going just in some random order. All right. Patel, I made you co-host. Charles, I made you a co-host too. Brad, I think I'm done with you, and Kevin, you should be all set. And let me check their first person. Okay. Pasarkar, you are here, and I'm making you a co-host too. Okay, cool. So we should be all set with panelists, I would hope. And yeah, let's get started. So what do I have on my agenda? All right. Well, first, just check with you how you folks are doing. Someone said there's a Fox exam tomorrow. Yeah, Liam, I don't think Shan selected you to be a co-host, a panelist for today. So did you get a message? Did you get an email from Shan saying that you are selected for this lecture? Because we have more people than we have the need for every lecture. So she's selecting a subset of the people who signed up. Is that making sense? You got an email saying that was for the 28th. All right, then yeah, let me make you a co-host too. And let me make a note in my notes to make sure that you get points for this lecture. I'm trying to keep everything updated. Okay. Yeah. So I Liam, I added you as a co-host. Okay. Are we all good with all the panelists? All panelists who think that they will be helping with Q&A today? Yeah, and we are starting MIPS today. So tomorrow on Wednesday, there is a very important lab. So I know, you know, people are saying that they have a Fox quiz and people are stressed about it. But hopefully you can still find time to go to their lecture, to the lab, no lecture tomorrow, to the lab. And because I think it's pretty important. And with MIPS, probably you have heard from your roommates, friends, whoever, that MIPS, can be, can be hard. So we'll try to start slow, but still, if you've never done any kind of assembly, low-level programming, that can be hard. 8 a.m. Really, for Fox quiz? It's at 8 a.m. Wow, that's brutal. Oh, wow, yeah. Well, I'm sure, uh, you will do just fine. And then Fox is fun in a way. All right. Well, yeah. You don't agree that Fox is fun? Um, yeah, I think I don't know. I co-taught Fox only once with Professor Malik, and yeah, my impression was students generally liked it. So, all right. Anyhow, good luck to all of you who have this quiz, Fox quiz, tomorrow morning at 8 a.m. Good luck, folks. But let's now talk about our matters. One thing about lab that I wanted to mention, and I cannot stress it enough, is when you are in the lab, your lab TA and lab mentors are there to help you and answer your questions and explain things to you. So they're not there just to mechanically, look at your code for the checkpoints, to give you the checkpoint on Submitty and let you go. Okay, and it's in your best interest to actually torture them with questions about the material, so that anything like mentioned in the lab handout is clear to you, all of you, each of you, and has been explained. Because that stuff that is in the lab handout may actually pop up somewhere else, like on the exam. And this is, I'm talking about this for a reason, because if you remember our previous lab 2, there was like a paragraph that somewhere in the middle was saying, well, look at the file that we provided with the data, so that binary file with some obscure contents, and try to decipher that file, try to look into that file using the tools like hexdump and the like. So then, because of that, I was assuming that people would be familiar with hexdump because it was advised in the lab that people, do run a tool like hexdump and look at the output and understand what that output means. And of course, hexdump works with files. So my expectation was that, people are familiar at least with their, formatting of the dump. And then in addition to that, there was also one of their practice problems for the exam that was that was saying, please write a memory dump function. That was following the formatting of the hex dump with a -c flag. Because of these two things, I was largely assuming that students would be familiar with, the concept of the hex dump, and would not be scared, about when they see hexadecimal values. And we haven't spoken yet about, how those hexadecimal values can be converted to decimal and that kind of stuff. But in general, the idea that we can represent numeric data in different systems with different base should not be new. My expectation was that it should not be new to the students, and that's why on their exam, you all know that this question 2 was appeared, and it was exactly built around the idea. So we show you the hex dump, we show you the memory dump, which is the same format as the hex dump. It's just the data from the memory, and we ask you to identify the pointers and where different parts of arrays are located. I was told by several students that that question came as a complete surprise to them because they've never seen hex dump before, they were not familiar with the format, and they would just honestly scared and intimidated by that question, and that certainly was not my intention. Okay, and and it's for this reason, it's important for me to get feedback from you how things are going in labs. And like I said, please make sure that that everything that even mentioned in the lab is explained to you. If you don't understand what it means, ask your lab TA, ask your lab mentors. They are there for that exact purpose. Yeah, there was a reference to hex dump in the previous lab 2. Okay, because and if the TA says not to worry about that, well, tell them that it's their job to explain stuff to you, or if they're not able to answer right there and at that time, they should find an answer and forward it to you, or give you a specific pointer, a specific reference to to the answer for the question that you're asking, right? So everything that is in the lab handout is there for a reason. Okay, so let's please be more proactive and treat lab as another preparation for the exam, as another opportunity to practice all the material, because it may actually pop up somewhere else. Yeah, I know it can be hard, you versus the guy who tells you not to worry about. Let me know if that's the case, okay? And if any of our TAs, mentors, need some additional training about how to handle student questions, we will certainly do that internally. But if I'm not aware of any problem, then I won't know that some action is needed. So it's important that you give me that feedback if anything is not exactly right with with labs or with anything else. Okay, is that making sense? I'm more worried about the Unix shell scripting. Yeah, so that's the other thing that when I was writing this exam, so it was funny. For the first question, there I had a few fairly complicated lines. Remember that first question, you had to identify where each pointer that is printed, which segment of memory it is from, text code, data, stack, heap, and so forth. So I wrote the stuff that I wanted, and then I thought, oh, it would be nice to have like 1 point per line of output. So I needed a few more printfs just to make sure that there are 19 of them. So effectively, I needed a filler, and I was thinking, well, I really want to give them a free point. So why don't I do printf pointer of ampersand main, because that would be like a free point. Everyone should get it right. And then when I was looking at their at the actual submissions, I was just horrified because very few people got that that part of the question right. So very few people realize that main is a function. So what is a function? It's code. So if I take the address of main, it's going to be in text code, and so you see how different my perspective can be from yours. Something that I thought was a free point is probably going to be a loss of a point for many of you. So it's important that you keep me posted about your perspective, your view of the of the things, and things that are hard for you, because I may not actually realize that they are and that they need further work. And this kind of brings us back to our poll from last lecture. Let me start sharing something. Let's go over that poll, or those polls from last lecture. Okay, and I need to okay. in the chat. Okay, yeah, and I was just reading the chat. So why are there so many typos in the exam? Well, because exams are written by humans, and one of them is sitting in front of you virtually. So humans try their best to not make any mistakes on exams, but sometimes they do. And hopefully, most of those are not really changing anything. Like if you think about the previous exam, one was a formatting issue, so the white space, um, moved to somewhere it was not supposed to be. Another one was the value to initialize the elements of the array, the formula. It largely didn't matter because we were telling you the values in the arrays. So the printfs with the arrays, with the array values were given. So largely the exact formula didn't really matter that much. So hopefully all those, and then in question 3, the name of the file was given incorrectly, input instead of output. But we would not penalize, of course, for any of those typers. So even if you wrote your script redirecting input to stdin and redirecting output to the same file because it was our typo, you would certainly not be penalized at all. And so regarding the practice, so someone was saying something that, yeah, for the data segment, we didn't have a lot of practice. We mentioned it in their lecture, and so there was an example that we went over when there was a global, some global variable, and we mentioned that it's in the data segment because it's global, and it was certainly in the slides as well. Okay, so that was that. Hopefully, I answered that concern. I addressed that concern, at least to some extent, and. Yeah, one of the panelists was saying that they are still unable to access Q&A. So they were expecting that they are that they received an email from Cheyenne about today's lecture, and they still are not able to access Q&A. Yeah, if that is the case, please let me know, because if you mentioned before it's scrolled, I would be able to find it quickly. Could we get harder practice exam questions? Sure. Yeah, that we can do. Definitely. And well, harder or more aligned with exam, it's kind of hard to define more aligned with exam. Like giving the exact same problem as on their as in the practice exam, just with different values, is not going to make a different question, right? It's going to be the same question with just different values. So that's make it hard. That makes it harder to kind of align the questions because the questions have to be different. And need practice that is comparable, difficult to what we are expected to know in the exam. Yeah, and that is the challenge that I was talking about before. So, for example, for question 1, there was a practice problem that I think was the same difficulty. It was just a little shorter on the practice exam, even for exam 1, but then it didn't make it to exam 1 because we haven't covered the material. So it was included in exam 2. Okay, and it was a practice problem exactly like that, with just not 19 printfs, but 5 or 6, give or take. And okay, Kevin, I think I made you a co-host already. Can you? Are you sure you cannot answer Q&A? I can verify again. Yeah, because you are on my list of co-hosts for today. Anyway, I just made you a co-host again. Let me know if that fixed it. So for question 2, that was based on the lab and the practice problem, where you were supposed to write the memory dump function. And for question 3, that was based on our conversation from the last lecture before the exam, right? When we went over the example of writing a script that compiles and runs your code in the last lecture. So, I'm not saying that it's your fault that that you miss it, or that you were not prepared enough, right? It's just the importance of you giving me feedback about what your troubles are, and that's exactly what we are kind of doing right now. So so finally back to the poll results. So that was that kind of speaks for itself, right? So most people found a test 2 to be at least somewhat harder, and a lot of people found it significantly harder than test 1. So that is certainly going to be taken into account as we are preparing for exam 3. And yeah, I'm seeing the comments about making their practice problems harder and releasing the solutions earlier. I don't want to release them too early, but I will try to release them earlier than we did for exam 2 for sure. I don't know what the average might be for exam 2 because we are still grading it. We are currently at about, as you can see, at about 20-ish, yeah, 18% done. So it's unfortunately far from being done. So our TAs and mentors who are helping them are working hard on trying to get it graded quickly. So don't look at the averages for the problems yet, because if only 5 submissions out of 250 are graded, it tells you nothing. It's statistically insignificant, and those numbers can change. So don't look at those numbers yet. We are still tweaking the penalties, the number of points that we give for certain errors, and that kind of stuff. Okay, and there was a request for a review session on practice problems and such. So we already have this review session, and it's your lab before the exam. Okay, so again, I'm not there with you and lab TAs, but please let me know if those review sessions are not exactly helpful, and if you have any ideas of how to make them more helpful. Right, so we have those review sessions, those labs before their exam are designed exactly to go over practice problems and answer any questions, and overall prepare you folks better for the exam. Okay. All right. So second poll, we were going over polls, and yeah. So that was this problem here, and I actually don't agree, and as you can see, the majority of students voted for for the option that it prints, all the 2021 24/9 comp work, which actually don't agree. So can someone explain why this is not really the correct answer?
Like, you want us to verbally explain it?
Yeah, either way, since verbally is perfectly fine, or if you're more comfortable in the chat.
So I put it prints 3 integers and then something else. That is correct, correct?
That is correct.
Yeah. So it prints 3 integers, that being I, J, and K. But the reason that buffer looks weird is because doesn't what does buffer refer to? I can't remember. Buffer is something where I think it's an address or something, is it not? I can't
Yeah,
remember.
so buffer is this array of 80 characters. So it's statically located. It's right here. So it's the stuff where whatever whatever we read from the file, it gets there, or whatever we print. So here we
Oh no, I
print
can't see what it
that.
was assigned to on your screen because like the text is really small, which is why I was asking what buffer got like set to. Like I'm trying to zoom in and my computer is just like, yeah, no, we're just gonna make the resolution worse.
Okay, so I'm zooming in. So first we scanned from the buffer into those variables. Okay, I, J, and K. So what did what was forgotten? Um, okay, yeah. So there are several things that are wrong, right? One, someone noted it's W plus, which means that the file is open for writing, and if the file exists, it's overwritten. So here it would help um, if you look up the modes for fopen, and if you scroll to W plus, it creates an empty file for both reading and writing. So since it creates an empty file, there's no data there, right? So we would still be able to execute scanf, but the values would be just junk. And even if we had this file open for reading, this line assumes that, well, first we read the entire line of text from the file into the buffer. Oh, hold on, no, this is fscan. Never mind. Yeah, we're good. So it reads from this my file. Yeah, so it's their mode. It's the W plus here. Okay, is that making sense? And you can just copy this code and run it. Well, scanf would work. What do you expect it to do? Remember, scanf and all friends of scanf, fscanf, sscanf, and whatnot, they return the number of values that were successfully read. So in this case, it probably returns 0. But it doesn't mean that it's not going to segfault or do anything nasty, right? So if you ignore the value that it returns, you're never gonna know how many values were read successfully into IJK. But their idea is IJK are values that that have some specific values, right? They cannot they cannot contain nothing. But if nothing was read from the file into IJK, then IJK would contain their original values. And what are their original values? They can be anything. We don't know. They are undefined because we never initialize them here. Okay, is that making sense? So that's why it will, and then when we print those values, some values will get printed. We don't know what they are, but it will be 3 integers in the string because fprintf doesn't have a choice. It will print whatever IJK and buffer contain. All right, so yeah, pay attention to this mode that is used to open the files. And then number 3 was, yeah, so those are here I agree with Vox Populi. The parent will exit, all children will stay, they will continue execution, and when they are done executing, they will turn into zombies. That means that they will still hold a row, hold a position in the table of processes internally in the operating system. So they will occupy PID, but they will be essentially done. They will not be executing any code, but they will stick around until something purges them from their table of active processes. So such processes are called zombies. Okay, and so what is the difference between W and W plus? That's a good question for the Q&A. So please ask it here, and one of the panelists will link documentation to fopen and or explain it. Explain it in more detail. All right. So this is really the thing that we just went over. Okay, so W is only for writing. W plus is for reading and writing. That's the short answer. Okay, we good? Okay, so those were our polls from last time, and we are continuing with. Let me check if there was anything that I wanted to talk about. All right. Okay. One thing that I added to our course materials, which we will need today and really for the next month, maybe even more. So it's a very useful reference card. It's here in the reference materials. So this is just a link. I think it's pretty useful too, but this reference card is so if you have a paper textbook, it's in the paper textbooks, and it's a kind of tear out thing, so you can just tear out and use it as a reference card. I think it's kind of green, at least it's green in my copy of their textbook. But here's the PDF for it, and it is loaded with information, as you can see. I don't expect you to kind of grasp all of it at once, but over time, please keep referring to this card because it contains a lot of information in a very concise form. It's a little cryptic, but if you figure out and of course I will help you with that. If you figure out the format and the conventions, then it's extremely powerful because it's very concise. Okay, so this is about MIPS, which we will be starting today. And you see memory allocation. So here is your stack data text, and there's also heap, and there's there is a diagram for the stack frame. We are going to need all that stuff, and this is why actually we were paying so much attention to their pointers and addresses and memory segments in the previous topic when we were talking about C, because that same stuff is going to be important, and probably even more important here in MIPS, because in C everything is kind of taken care of you. It's a high-level language. It takes care, it hides some unnecessary low-level details from you unless you really want to look into them. And at least in C, you can look into that, right? In some other languages like Java, you would not be able to really get a reliable memory address of a certain memory location, right? It's hidden even more. Here in MIPS, you will have to deal with those low-level details yourself. So you need to definitely have a very good understanding of different memory segments to understand how your program runs, and just from the pragmatic point of view, to know how to debug your program. Okay, so that's that. Please refer to this reference card, and so that was one thing that I wanted to mention. So exam 2, we already talked about grading progress, and homework 2 due on September 30th, and we will go over quite a few examples in today's lecture about performance computation, and hopefully that will help you a lot with the performance problems on this homework, right? Because really, and I know I've been criticized before for saying, "Well, it's so simple. I'm sure all of you can do it." And then students come back to me saying, "Hey, it wasn't simple at all." Well, I can see your perspective. Things may not look simple, and many things are really not trivial, especially when we get into MIPS and memory hierarchies and the internal design of the processors. But for performance computations, I think they are actually not hard. It's a few formulas, and you just have to understand what these formulas stand for, and then you just have to twist those formulas, so that you you are able to determine the quantity that the problem is asking about. So if you find uh, all the computations related to performance hard, that's okay. But I'm still confident that all of you can master that topic. Okay, so let's go back to our topic. I think that's where we left off. And that's one of very simple formulas, and hopefully you are able to deduce those formulas even if by chance you forget them, right? So we have the clock, this synchronization that allows our all components of our system to kind of work together, that we in sync with each other, that we discussed before, right? So this is our master clock, and clock has a period, right, which we call clock cycle time, and if we know the number of clock cycles, some action, some task took, we just multiply clock cycles by clock cycle time and get the CPU time. Yes, LaTeX is recommended but not required, but you are required to, to submit, to type your answers, right? You cannot handwrite and then scan. So we want, you can use your Word or any text editor or whatever, but you then have to turn it into, a PDF from from what you've typed. Yeah, so someone I think mentioned that I believe, depending on who your professor for Fox is, some of them actually require LaTeX. So if that is the case, then it's even easier, right? So you're going to be using LaTeX for Fox and this class, but we do not require LaTeX. Okay, I think it's a good idea. I think it's a good moment to learn LaTeX if you haven't already, but it's up to you. And no, handwritten PDF is not okay. So it has to be typed and in some word processor, text editor, whatever, but it has to be typed and then turned into a PDF. Okay. So that's our one of our formulas. Hopefully, pretty easy, making sense. And here is an example. I think that we went over last time. So basically, using that formula, we have one computer with 2 gigahertz clock, and let's say a certain program takes 10 seconds, and then we want to design another computer on which that same program runs in 6 seconds. And we can do faster clock, but if we do that, we go with 20% more clock cycles. Okay, so the question then, how fast, what the frequency of the main clock of computer B should be. Okay, here it is. We plug it in. It's 4 gigahertz. Why? And why it makes sense intuitively? Well, because if you look at and then it's just a general advice. Once you got an answer, look at that answer critically and see if it is making sense. Do this quick sanity check. Like, we plugged in all the values into the formula, and we got that we need to make computer B run at 4 gigahertz, and so that tells us, oh, computer B should be, twice the speed of computer A if we just look at the clock, right? It's 2 versus 4 gigahertz. So then, how come our program runs not twice as fast, but it runs faster, but by a factor less than 2? Well, that's because we by increasing the clock rate, we had to compromise, we had to sacrifice their clock cycles, and so that was our design limitation that we were aware of, that we were given, that if we go with a faster clock, we get 20% more clock cycles. So that 20% is exactly the difference between 5 seconds that we might have expected, if not for this 20% increase in clock cycles, and the actual running time that we get. So it's 6 seconds. So yes, computer B runs twice the frequency, but it has 20% more clock cycles, and that's why the same program takes 6 seconds instead of 10, not 5 as we might have hoped. Okay, and then so we have instruction count, which is just the number of instructions in the program. And once we start talking about MIPS, you will see exactly what an instruction is. For now, you can think of it as just one minimal statement in your code, right? So one minimal command that your program contains, and you have a certain number of those commands that we call instructions. And then, of course, there is a certain number of clock cycles of the CPU per instruction. So, that number can actually be different for different instructions. You can imagine some instructions are probably very fast and they only take 1 cycle to execute, but some other instructions, like let's say division, may be taking much longer. They may be taking 10 cycles. So of course we have to take the number of clock cycles per instruction into account when computing the total clock cycles to execute a certain program. So if our program is 100 instructions and each instruction is 2 cycles, then overall this program will take 200 clock cycles to execute. So this is the first formula, right? And then CPU time is instruction count times CPI, clocks per instruction. So this is our first formula, clock cycles, times clock cycle time. So in our previous example, if we had our program that we computed would take 200 cycles, and then if each cycle is, let's say, 1 second, then their total CPU time, the amount of time this program would take to execute on CPU would be 200 seconds. And of course, clock cycle time of 1 second is completely unrealistic. So as we are talking about nanoseconds, right? Because their frequencies are in gigahertz. So it's 10 to the 9th. So the duration of 1 clock cycle would be on the order of 10 to the negative 9. But for the sake of this simple example, it was just easier to go with seconds than deal with nanoseconds. So instruction count for a program. What determines that value? Well, first it's the program, right? The longer program will likely have more instructions, but then the compiler, of course, because the compiler determines the how the program is translated from your high-level language into the actual machine instructions. And ISA, instruction set architecture, that's the set of instructions for a particular processor, for a particular hardware. And of course, different architectures will have different instructions, and that of course determines the number of instructions in a program. So for example, if your program needs to multiply two numbers in memory, if your architecture allows multiplying values directly in memory, then of course there is no such architecture, but let's imagine for the sake of the argument that there is, then this multiplication will take just one instruction. If your architecture requires that all values are multiplied in the processor, and therefore if the values are in memory, they first need to be moved into the processor, then of course it will take more instructions to perform this multiplication. You will need to move the first operand to the processor, the second operand to the processor from the memory, then perform multiplication, and then store the result back into memory. Definitely more than one instruction. And this cycles per instruction, as we mentioned, it may depend on a particular instruction. So different instructions may have different CPIs, and that's why we are quite often interested in the average CPI, for example, for the entire program. And the program is a mix of instructions that all have their different CPIs. So we can partition all instructions into classes, where each class would have a particular value of the CPI. For example, load store instructions may have one CPI, one clock per instruction, and division might have four CPI. Four might require 4 clocks per instruction. And of course, their average CPI is determined by CPU hardware for the most part. If the same CPU gets its clock rate halved, when then the speed gets halved. Yes, if no other changes are made. But like we were mentioning here, maybe if you want to go with a slower clock, it would, because the clock is slower, it would actually allow you to use less clock cycles. So instead of having 1.2, you might be down to 0.8 clock cycles. So you can actually make your programs take fewer clock cycles. And yes, each clock cycle will be longer, but because of the fewer clock cycles, the difference may not be exactly by the factor of 2. Yes. So if we are talking about the same processor, no, not comparing, two architectures, computer A or computer B, but if you just, take your computer and that runs at, 4 gigahertz, and run it at 2, it's going to slow down by exactly a factor of 2. As far as CPU is concerned, of course, there are other considerations like memory, because memory is usually clocked differently, so it runs at a different frequency. So that makes the complete analysis more complicated. But if we are only talking about the CPU, then yes, clock is exactly the rate at which instructions are executed. If you make it half of what it used to be without making any other changes, then the amount of time it takes for the same program to execute will go down by exactly the factor of 2. Will go up. The time will go up by exactly the factor of 2. All right, and we have our first pop quiz. So here, think about the CPI that we just discussed, and think about all those factors that may influence the CPI. So which of them do you think may potentially influence a CPI? For example, going with a different algorithm for your program, might that potentially change the CPI of a program, and do the same kind of analysis for all the other factors? So let's open our first pop quiz. And moving on, so here is an example of the computation. And so, by the way, all those examples are also in their textbook and in Zybooks. So in Zybooks, if you just go to this chapter 4, section 4.6, performance, then, oops, yeah, the first poll is about RAM price. Thank you. Let me close it for now, and let me. Is this the? Yeah, we'll go back to RAM prices. But is poll number 2 the right one? So, okay, it didn't open it, did it? Lecture 8, poll 2 should be open. Interesting. Huh. I know. Let me. And accepting. Oops. Something went wrong. Please try again. Hey, Submitty developers, help me out. It doesn't even tell me what went wrong. Something went wrong. And it's stuck. Okay, and then it cleared all my checkboxes. Let me try one more time. And let me. Okay, it looks like it is open now. Yeah, so poll number 2 is the right one. Okay, and I was saying that if you go to your textbook or your Zybooks, so all those examples are reviewed here, and some of them with even more explanations than than I'm giving you. So if you need kind of more in depth, you can look here, and so that's the example that we just I think are about to review. 250 and 5 picoseconds. No, it's not the one. Where is? Yeah, so that's the one that we are reviewing right now. Okay, so. And the idea here is that we have cycle time, which we know is the inverse of the frequency. So computer A, computer B's cycle time is twice as long. So computer B is slower, by the clock frequency, but it has a smaller CPI. Okay, so on average, and this is the average, so that means that on average, each instruction on computer B is only 1.2 cycles, and on computer A, it's 2 cycles. All right, so more cycles on average per instruction on computer A. So the question is, does it really balance out the shorter the shorter clock cycle, the higher frequency, and so here we just need to compute, and so we use our formula instruction count, which we don't know how many instructions, but it doesn't matter, right? We can say, well, instruction count is some I, and 2 clocks per instruction, 250 picoseconds. So it's I times 500 picoseconds. That's the CPU time on processor A, on computer A. We do the same for B, and we see that it's 600 picoseconds. And that tells us that, well, despite the fact that computer B is twice as slow if we just look at their frequency, at the clock cycle time or at the clock frequency, it is actually only 20% slower than computer A because it has a much smaller CPI. Okay, so yeah, picosecond is 10 to the negative 12th. Thank you. Yep. What would be their, how can you kind of, see if that makes sense? All right, you can actually, and let me just switch to my calculator. Okay, so you can just do very simple computations. Like if we ignore CPI and I'm comparing two computers, 500 and 250. It's a factor of 2. So we would expect computer B to be 2 times slower, but we know that there is an additional consideration here. So we have 2 divided by 1.2. 1 point, well, it's probably going to be easier. Right, so there's an additional 0.6 factor here. Okay, so that means that one factor makes computer B slower, our cycle time. The other factor makes it faster. So if then we do our one factor 2 times our second factor 0.6, you get exactly this 1.2, which means yes, it's slower, but not by a factor of 2, but only by 20%, because there's this huge difference in clock cycle time is partially made up by a much better CPI of computer B. Of course, the fewer clocks per instruction, the better, right? The faster our programs will run if they require fewer clock cycles per each instruction. Is that making sense? I just want to make sure that you you get this idea that yeah, there are formulas, but you need to understand where the formulas are coming from, and the formulas need to make sense. Also, as with any any problems that involve units, make sure that your units match. Just look at instruction count. All right, that's just a number. CPI is just a number, and cycle time, this is in seconds, right? In some units of seconds. And the resultant quantity is CPU time, which should be in seconds. So make sure that your units are what they should be when you use a particular formula. Yes, understanding that an nanosecond is 10 to the negative 9th, this is something you certainly expected to know. Okay, and now probably the last complicating factor that we are going to review is that different instruction classes may have different CPIs. So what do we have? What do we do if we have, if we have this case, not all instructions are equal? Then we just have to look at our program and compute their clock cycles separately for each type of instruction based on the CPI. So we use the sum, right? So imagine that there are instructions that take that have CPI of 1. So we take the CPI of those instructions 1 and multiply by the number of such instructions in our program. Let's say 200. So it's 200 times 1, it's 200. And then let's say we only have one other group of instructions that are slower and they take 10 clocks per instruction. But we only have 2 such instructions. So we take 2 times 20, that's 40, and we sum. So the total clock cycles of our program is 240. And then based on this, we can compute the average CPI for the entire program, right? But that's how we do this, the summing for all the instruction classes that or instructions, instruction groups that we have based on their CPI. And so then if we just divide it by their if we take the total clock cycles, divide by their instruction count, we get the average CPI, but it's weighted average, right? Because of course it matters how many instructions we have, right? If we have fewer slower instructions, of course our average CPI will be better, will be mostly determined by our fast instructions with lower CPI. So that's why it's a weighted average. Okay, and here is a CPI example with exactly this case. There are three classes of instructions. We call them ABC, whatever that stands for. And we know that instructions from class A are very fast. They only take one clock cycle. Type B instructions are slower. They take 2 clocks per instruction. And C is like the slowest. Let's say it's like division. It takes 3 clocks per instruction. And then we have two, let's say you compile your program with 2 different compilers that produce different code. For the same source code, different compilers may produce different machine code. And so we have to compare them. So we have instructions in result 1, instructions in result 2. And imagine that the first compiler produced the code that has 2 instructions of type A, 1 instruction of type B, and 2 instructions of type C. And for the second compiler, it's 4, 1, and 1. So can you tell which which is better without computing? Probably not, because yes, if you look at the total number of instructions, then our first compiler only used 5 instructions for this program, and our second compiler used more instructions, 6. So just the total number, the sheer number of instructions is worse for compiler 2, but the majority of instructions that compiler 2 generated are those very short instructions that take only 1 CPI, whereas the first compiler used more of the slower type C instructions. So we have to compute and see whether their overall reduction in the number of instructions balances out the fact that there is a different composition of instructions that use different CPIs. So we just use our formula from the previous slide, and we have 2 instructions of type A, so 2 times 1, and then 1 times 2 right here, and then 2 times 3 right here, and the total clock cycles is 10. And because we had 5 instructions, the average CPI is 10 divided by 5, it's 2, right? It's 2 clocks per instruction, that's the average. And then for our second compiler, so we compute our weighted sum, so it's going to be 4 times 1 plus 1 times 2 plus 1 times 3, and it's 9. And the average CPI turns out to be actually better, and the total clocks to run this program is actually shorter. It's 9 clocks instead of 10 clocks for compiler 1, despite the fact that there are more instructions, right? Yes, there are more instructions, but the total number of clocks is shorter because we used more shorter instructions, and we were able to reduce the slowest instructions from 2 to 1. Okay, so that's the idea, and here is the formula that kind of captures it all. The way you read this formula is to compute the CPU time for a particular program. You first need to know how many instructions there are in this program, so it's instructions per program, and then you need to know your CPI, clock cycles per instruction. And it can be easy if all instructions have the same CPI, or it can be a little bit more involved if you have to do this weighted sum. And for that, of course, you need to know how many instructions of each type you have in your program. And then you have your seconds per clock cycle. This is your time clock. Okay, and yeah, so I know poll is still open. Okay. And yeah, I'm not gonna comment. I'm not gonna comment on this, but yeah, it was intentional. So that's not cheating. That's just, remember, polls are just for you to test yourself. And if you had to change your answer, that maybe is a sign that you need to kind of um, think a little bit differently about those things, right? Or something like that. So it's like I said before on multiple occasions, those polls are largely an attendance instrument than really to test your understanding on something that we just covered, right? It wouldn't be fair to give you, problems, questions as hard as the ones that you would find in homework assignments or in on exams. All right, and here is another pop quiz for you. So we have a Java program that runs in 15 seconds on some processor, and then there's a new compiler that you want to try, and you know that it would generate for your program, uh, you know, only zero point 0.8 instructions as compared to the old compiler. So for old compiler, compiled your program and used 100 instructions, this new compiler would only, for the same program, it would generate 8 instructions. And unfortunately, nothing is free. So, any benefit is, at least partially counterbalanced with, something bad. And this is no exception here. Their CPI will increase by 20% for this new compiler. The question is how fast in seconds can you expect your program to run if you use the second compiler? And let me open that poll. Okay, hopefully you can see it now. Okay. Yeah, so if programming languages affect CPI, which is the best worst programming language in terms of CPI, you cannot tell because programs are complex. Usually there is no single best or worst ever for all possible purposes, right? So for a particular program, you may find that one works better than the other, but it doesn't mean that it would be true for all programs. And that's why many programming languages exist. Is it again the wrong ball? Oops, let me. Hopefully I got this correct. Yeah, thank you. Okay, yeah, and if your math doesn't match any of the options, but you're sure your math is correct, maybe it's option D, who knows? All right, that's pretty much all we wanted to talk about the performance. Here are a few examples, additional examples that I have in lecture notes that are related to this topic. So let's review them. So first is the definition of performance. So if we, when we are measuring performance, we usually want a metric that reads as the higher the better. Okay, so in that sense, time would not be a very convenient performance metric because the longer your program is running, the worse it is, the worse performance is, right? You want the opposite, so we can invert the time and take it as the measure of performance, because then the shorter the time, the higher your 1 over time is going to be, and that means we are back to our convenient paradigm that the the higher the value is of the whatever performance metric using, the better performance is. All right, so very quickly, let's go over those examples. We have two processors. One takes 20 seconds, another takes 50 seconds. Which one has higher performance, and by by how much, or by which factor? You can just dump your questions in the chat real quick. I mean, dump your answers in the chat, of course. So does X have higher performance, or Y? X, right? By how much? 2 times fast. Exactly. All right. So let me. We want to compute speed up, which is performance of one divided by the performance of other. We just mentioned that we want performance to be the higher the better. So we take 1 over time as our performance metric. And yeah, it's 50 seconds over 20 seconds. It's 2.5 speed up. All right. Then we have this formula about their CPU clock cycles and the clock rate. We have processor with a clock of 4 gigahertz and a task that requires 2 billion cycles to complete. So how long does it take for this process to run this program, this task B? Please give me your answers. Half a second? Yep, because in 1 second, this processor will execute 4 billion cycles, and our program is only 2 billion cycles. Half of that, exactly. 0.5. Job. So do you agree? It's easy so far. It's not that convoluted, right? So half a second. All right. So number 3, we have 2 processors. A that completes some program in 2 seconds, and B is the we have hold on, sorry. We have one processor that runs a program in 2 seconds, and this program is 8 billion cycles. So what is their clock rate? 4 gigahertz. How did you get it? Obviously, right? You have 8 billion cycles in 2 seconds, so you have to run at 4 billion cycles per second to make this happen. All right, exactly. 4 gigahertz. So question number 4, we want to complete some task in 5 seconds on processor B. And we know that in processor B, we need to design. We have already processor A that that runs at 5 gigahertz. And we want processor B to run at 7 gigahertz, but it will have 1.5 times more cycles. It will use 50% more cycles to complete this task. So does it make sense to design processor B? Will it actually, will we see an improvement? No. Okay, exactly. Yeah. And here is why. Okay, so we have, we first compute time B 1.5. All right, that's our number of cycles. So it's 50% more than cycles of A divided by 7 gigahertz. That's our target clock frequency of B. And then time of B, we just substitute cycles of A, which is cycles divided by clock rate. We have that formula, and then we plug in the values for A, 5 seconds and 5 gigahertz. So it's 25 billion cycles, but on B it will be 50% more, divided by 7 billion cycles per second. That's their gigahertz frequency. We end up with 5.35 seconds. So it will actually run slower on processor B, given their given the limitations that we are that we have in this problem. All right. So next, CPI. Clocks per instructions. So here are the formulas from the slides, and here is their problem. So we have two processes, A and B. A CPI of 2, B CPI of 5, and then B's clock is twice as fast as A's, and then there is a program. There is a program that takes 10 billion instructions on A and 5 billion instructions on B. The question is, which processor is faster for this task, for this program, and why, and by how much? Anyone? And then let's just look at that intuitively. So B's clock is twice as fast, and for B we have also half the number of instructions. So the program, that same program, is actually shorter by a factor of 2, and it is instructions are running at twice the speed. Okay. All right. That's a lot. I know. That's where math gets a little bit more complicated, but hopefully not by much. All right. Let's. All right. So we use the same formulas as before, right? So on processor A, we have 10 billion instructions, 2 cycles per instruction, and divided by clock A, whatever that is. So it's 20 billion instructions divided by clock A. And on time B, it's 5 billion instructions times 5 cycles and divided by clock A times 2, because our B runs twice as fast in terms of their frequency as A. So we get 12.5 billion cycles per clock of A for the time of this task on processor B. So we see that B is faster. And then next question is, how much faster? By which factor? So we just divide these two times, time A time divided by time B. So that's the definition of speed up, how much faster A is compared to B. And it is 1.6. So and actually, so this is the formal way of doing this. You actually could skip all of it and just look at the numbers here, right? So we see that our processor B has so their clock cycle is 2 times better, right? The frequency is 2 times higher than that of A, and also we have fewer instructions by a factor of 2. So 2 times 2, it is 4. And then the only other thing, so this is just in terms of their benefit of B compared to A. So, but then we have 5 and 2 for CPI, right? So the CPI of B is actually much worse. By which factor? By a factor of 2.5. Okay, so we do 4 divided by 2.5, 1.6, right? So you can almost think of it as just turning different knobs. You have 3 knobs, right? So you're looking at processor B. It has 2 times better clock cycle. It has 2 times better number of instructions, and it has 2.5 times worse CPI. So it's 2 times 2 divided by 2.5, 1.6. Okay. So that's that. And finally, I think the most convoluted, that is problem 6 with different types of instructions or different classes of instructions. So we have 3 classes: memory bound instructions, arithmetic like add instructions, and logic instructions. And we are given their CPI for each class for each of the processors. Okay. And you see that the blend of instruction classes is different on different processors. On A, we have we have a lot of memory instructions, and so on. Uh, we have different CPIs for different instructions. So as you can see, memory instructions are much slower on A than other instructions, right? By the factor of 5. And on processor B, it's not as bad. It's only by a factor of 3 at most. But the price that we pay for that is that addition instructions are actually slower than logic instructions on processor B. On processor A, they execute the same 1 clock per instruction. On processor B, addition is slower than logic instructions. Okay, so now we have to compare which processor is faster and by how much. Any thoughts? Blocks are also different, and we know how many instructions are there in a particular program. Right, so that's the composition of of the program we are interested in. All right. So we just use our formula. So on processor A, we just do our weighted sum, 2 billion times 5 billion times 1, right? So we are computing time. So this would be the total number of clocks, and then we divide it by clocks per second, and we get 4.75. And when we do the same for processor B, turns out it's 8. We see that processor B is actually slower by the factor of 1.68. Okay, so it's quite significantly lower, right? If we just compare 3 and 4, we see that it runs only slower in terms of the clock cycle by a factor of 1.3 roughly, but it is actually executing programs slower by a factor of 1.68. I mean, this particular program, of course, if the composition of instructions would be different, it would change things, right? But we see that it is it is slower because we see that there is a their amount of memory instructions is higher, and we optimized memory instructions for processor B, but it's not sufficient to to kind of outweigh their decrease in the performance that we had to introduce for addition instructions. So addition instructions run 50% slower than they were in processor A, right? Much slower. All right, so that's that. Now let's skip the rest of the stuff in chapter 1 for now. Right? It's of a little less importance, and we can always come back to it later. For now, let's look at our chapter 2. Okay. We have to cover chapter 2 because that's your lab tomorrow. So you need to know what you will be doing in this lab. All right. We are starting MIPS. So their instruction set, that's the first term that we need to talk about. That's basically their, I love this word, repertoire. what would be a synonym for this word? Can someone come up with a good single word synonym for repertoire? Skill set, vocabulary. I like vocabulary. Yeah, I don't think skill set matches exactly in this context. It would be like a nomenclature. I think that's another fancy word. So it's just a list of instructions of a computer, right? So, not all specific implementations of instructions, but just just a list of all the possible instruction commands, if you will. Yeah, I meant in the context of the slides. Yep. And of course, different computers have different instruction sets, and we've seen examples in our performance computations that different processors may have different ISA, so instruction set architecture. That's the abbreviation that comes up every now and then in the slides. And there are different even paradigms of designing instruction sets. You might have heard of CISC, or complex instruction set commands, and RISC, reduced instruction set commands. So those are different approaches to kind of having more instructions that can do very specific things versus fewer instructions that can only do basic things. But if you want to do something more more complicated, you have to use multiple instructions to achieve that. So that's the kind of difference between CISC and RISC. And RISC is a very popular architecture, so many modern computers have simple instruction sets with very few instructions. All right, MIPS is the architecture that we will be talking about. And does anyone know what MIPS stands for? Microprocessor, good. Yeah, million instructions per second. That would be my first guess. And when we go back to this topic of comparing performance and benchmarks, you will see that exact abbreviation MIPS used in it's a completely different abbreviation. It's exactly million instructions per second. So that's their one term, right? Which is different from MIPS that we are seeing on this slide. Here it's something like I don't even remember it myself, so it's pretty complicated. It's M stands for microprocessor, so your guess was right. Kudos to you. So it's microprocess without interlocked pipeline stages. Can you imagine that? I barely remember it myself, right? Basically, MIPS is an architecture for for processors, for microprocessors. All right, and so it's it's one of the most common architectures, maybe not the most common. So ARM is probably more common these days, but MIPS is still a very useful architecture, and it is simple enough to make it easier to study in a course like computer organization. And I know many of you will disagree with me once we cover MIPS, go into the details. I know many of you would consider it hard, but if it's any consolation, it's not the hardest architecture, right? So I think actually ARM would be ARM would be harder for someone who have never dealt with microprocessors before to grasp than MIPS. All right. So, what are those instructions? Well, you hopefully have a good picture of their of the compilation process that you've went through multiple times with C and C++. So you write your program in a high-level language, and then when you compile it, it actually gets translated into the instructions of a particular processor. So what we are going to be dealing with here in this part of the course is we'll actually look at what those instructions are. So it's like their assembly, if you've heard that term, right? It's like an assembly language for this MIPS architecture. And MIPS is just a type of processor, if you will. And there are others, of course, and we will also briefly look into their x86 assembly, which is x86 is an architecture that most of you are likely using in their laptops. All right, so let's go through some instructions. Those are like commands that you use. Those are building blocks for your programs. So addition is add, and this first part is called a mnemonic. And it basically, like the name of the command, it's usually very short, but it has a meaning that should tell you what this command does. For add, it's easy, and we will see that those mnemonics are also meaningful for other commands as well. And then arguments. So in this case, there are 3 arguments, 2 sources and 1 destination. So this command adds 2 values and stores them in the 3rd value. What are those values? Well, they are registers. So registers are special memory cells inside the processor that can store values. In MIPS architecture, all registers are 32-bit long, and there are 32 registers. And all operations in MIPS can only happen with registers. So if you have something in memory, you first have to move it from memory to registers, or you have to move stuff from registers to memory if you want to store anything. All right, for add, it adds the 2nd and 3rd registers and stores them in the 1st one. So all arithmetic operations have this form, and it demonstrates one of their 7 important design principles that we will go over. We summarize them a little later, which reads simplicity favors regularity. Okay, so we want something regular, and that means it will be simple. Maybe not the most efficient, maybe not tailored to specific, specific cases, but it's simple and regular, and that allows us to achieve higher performance. All right, so here's an example. It's not a real MIPS code, but we are getting close to it. So if we want to perform 2 additions, 1 subtraction, we have to run those commands. Again, those are not real MIPS commands yet, because those GHIJ, they refer to variables, not to registers, but we are 1 step from turning this into an actual MIPS program. And here is information about registers. So all arithmetic operations, they are performed on values in the register file. So register file is 32 registers, and each register is 32 bits wide. And so registers are numbered, but they also have names. Some of the names are given here below. T, so all register names are given starting, so they all start with a $sign, and then there are 10 T registers from T0 to T9. They're usually used for temporary values. There are also variables, so-called, there are registers for so-called saved variables, and they have this S in the name of the register, so S0 to S7. And the reason the processor is organized like that is because main memory is slow and it's huge. And that's, it's huge. That's partially why it is slow. It would be way too slow if we wanted to allow, let's say, multiplication across 2 memory locations directly. And that's why many architectures, they require that any multiplication happens between 2 cells that are in the processor itself, and those cells are called registers. So we can multiply 2 values that are in registers, like T0 by T1, and then if we want to move it to main memory, we can do so, but it would require a separate command. And of course, if we can avoid it, we should, because main memory you only want to deal with if you absolutely have to, right? If you are able to keep values, any intermediate results and any temporary values in the register file, you should, because that costs you nothing. If you want to load it to store it in the main memory, then it will be an additional instruction, and it will be additional clock cycles, and maybe multiple clock cycles, because again, main memory is slow. All right, so here's the real MIPS code where we assigned our variables to registers. So you see that F is in register as 0, and G is in register as 1, and so forth. In this case, just alphabetically. So our code then reads, take the value of S2, which would be H, take the code of S1, which would be G, add them together and store the result in register T0. Then take the values from registers S4 and S3, those would be I and J, add them together, store the result in T1. So we have those partial sums that correspond to the parentheses in T0 and T1, and we want to perform our subtraction. So we subtract T1 from T0, so I can just, so this intermediate result is in T0. This intermediate result is in T1, and we are performing subtraction here. So basically it's minus, right, between this and this, and the result goes into S0, and S0 we know is F, right? F is S0. So how we assign the variables to registers is kind of up to us. There are certain rules, there are certain conventions, but it's largely the job of a programmer to decide how this is done, and you will need to do this in your lab as well. All right, so memory operands. So main memory is used for, to store data that there's no way we can fit in the register file. So array structures, dynamic data. So we do have a heap in MIPS, but we're not going to talk about it today. It's a little more advanced, but we will get to it. No, don't worry. You will get your memory allocation, of course. So all arithmetic operations only operate on values from registers. So if you want to add two values that currently reside in memory, you first need to load values from memory into registers and then store the result back into memory. Memory in MIPS architecture is byte addressed, which means that each address identifies a byte, which is 8 bits. And there are also words in MIPS. A word is a multiple of a byte, and in MIPS architecture, words are 32 bits. It's a 32-bit architecture, so words are 4 bytes. MIPS is big endian, so we've talked about it before. All right, so here's an example of moving data between memory and registers. So we want to add H, which we assume is in S2 register, with the value of A8. A8 is the 9th element of the array. So 8 is the offset or the displacement, and because their architecture is 32 bits, this displacement of 8 needs to be multiplied by 4 because we have 4 bytes per word. So when we loading the word, and this is the instruction that is used for it, LW load word. So here we specify the offsets. That's the format of the command. The parentheses are part of the syntax. So S3 is the register that contains the base or starting address of A. That's where our array begins. And then we have to add 32 to it. We don't add it explicitly, but the offset is added to the base, the value of the base register automatically by this command. So when this command is executed, it takes the value of S3 internally adds 32 and takes their value from that memory address and loads it into register T0 so that we can then perform our addition between T0, which contains the value from A8, and S2, which is H, and store it into S1, which is G. Why can't it just be S1, S2, 32, S3? Because addition only works on registers. You cannot have addition in MIPS architecture that has an operand in memory. Okay, remember, it optimizes for the common case, and it wants to make this common case fast. Adding directly from memory is by no means fast. All right, so that was that example. And so what if we change this example slightly and we want to store the value not in the register, but back into memory, into this 13th element of A, which would have the index of 12. So the first part of the example is exactly the same, but for the third instruction, we use SW, store word, from T0, that's the value that contains our sum, and into their base address plus 48. Why 48? Because it's 12 times 4, right? We need to remember that each element is 4 bytes. We have 4-byte words. There are 32 registers, and you can actually, if you look at their simulator that you will be installing as checkpoint 1 in your lab, you will see like you can use Mars, you can use Qt SPIM, you can use text-based console interface SPIM. It's your choice. So here are those registers. Note how there are 32 of them, and each has a name: R0, A0, A1, T0, T1, and so forth. And you can also use Mars. If you use Mars, then those same registers are also listed. It's a slightly different interface. I will probably be using both of these simulators interchangeably, more or less, in this course. All right, so registers are much faster than their main memory, and that's why, because the architecture optimizes for the common case, it makes their addition and other operations only possible on registers. And if we want to move data to and from memory, we have to use separate instructions, LW and SW correspondingly. All right, so what if we want to add with a constant? There is an instruction called add immediate. It adds the last argument to the value of the register given as the second argument and stores the result in the register given by the first argument. So basically, we take the value of S3, add 4, store in S3. There's no subtract immediate, but we can easily do that by just adding with a negative number. There's a special register called 0. It is written as $0, and it's the constant 0. It cannot be overwritten, right? You wouldn't want a 0 to be overwritten on your system. All right, so that's the example. Basically, it moves, it copies the value from S1 to T2, right? Because adding with 0 does not change the value. So add is a real command. The command that you will often use called move is actually not a command. It's a pseudo command, pseudo instruction, because move is implemented exactly as adding with a 0 and storing the result in the target register. All right, so let's skip binary and hexadecimal for now, and talk about this part, and talk about the instructions that you will need for the lab tomorrow. So for the lab tomorrow, you are going to need conditional operations, and those are as follows. BEQ, branch if equal. EQ stands for equal. So what this command does, it performs a jump. So it's kind of in a go to. It moves their processor counter, the pointer to the currently executing instruction, to a label, to the code labeled with a label L1, if these two registers have the same value. RS and RT are just registers. B and E is very similar, but it's branch if not equal. So it jumps to L1 if RS is not equal to RT. J L1 is unconditional jump. It's very easy. It's just like your go-to, which existed in some languages, doesn't really exist in most of the modern languages, with a few exceptions. All right. So how do we write an if statement? You need the branch instruction, branch not equal, and if S3 is not equal to S4, and of course we need a correspondence between registers and our variables. So we say F is S0, G is S1. If they are not equal, we go to else label, and here it is. If they are equal, then we just fall through and we execute this addition, which is exactly what we need to do according to our C code that we are translating into MIPS. And then after we've done addition, we have to kind of go around this else clause. All right, if we skip this J exit, we would fall through and start executing the sub instruction, which is something we don't want. We want to go around the else part and go to the exit. All right, so don't forget about this unconditional J instruction at the end of the block to avoid fall through and executing something that you did not want. And then loops are similarly very similar. So loops are, it's basically their if and then with with a jump. So to the beginning if the condition is favorable. So what happens here, we are trying to translate this code into MIPS, and here is one new instruction that we kind of skipped over, but we'll come back to it. But for now, it's SLL, so it's logical shift left logical by 2. And if you remember, hopefully, I think, well, you're just taking Fox, so you may not even know that. But shifting the number by two binary positions to the left is equivalent to multiplying by 4. So you can just think of this SLL as quickly multiplying by 4. Why do we need to multiply by 4? Well, because S3 is our I, and we need to access this array, save I, and we previously saw that you need to multiply their offset by 4. All right, because MIPS uses 32-bit words. So that's this SLL. Then we perform our addition. That's this part. Hold on, no, we are adding T1 with S6, and S6 is their base address of 6. So we are computing their effective address of save sub I, and then we load from the memory from this address. So we load save sub I into T0. Then we check if T0 is equal or not equal to S5, our key. So if not equal, we are done with the loop and we exit. If they are equal, we execute the body of the loop, this addition. Right, so it's an increment. There is no increment instruction, so we just have to add the immediate value 1, and then we jump back to the loop, to the first, to this loop label, to the first operation in the loop. All right, so that's the basics of MIPS. So basic block is just a sequence of instructions with no branching, so no outgoing branches, no incoming branches, so no branch targets. And SLL is shift left logical. It multiply if you do it as in this example, shift by 2, it multiplies this value by 4 and stores it in here in T1. All right, and here are more conditional operations that you will see in the lab. So SLT stands for set the value of RD if less than. So RS and RT are compared, and then RD is set or not set depending on the comparison. SLTI is the same except for the last operand is an immediate value. So it's very convenient to use SLT with a branch, as this example shows. First, you set T0 depending on whether S1 is smaller than S2 or not, and then you do BEQ or BNE on T0. All right, so that's yeah, and that's pretty much all that we have to know, I hope, for our lab, and our time is up. So thank you, folks, for attending this lecture. Hopefully, yeah, I know it was packed with lots of new information. Hopefully, you have time to digest it. Please ask tons of questions tomorrow. Your lab, right? Remember what we talked about the lab before. Ask your TAs and mentors. All right, they are there to to be tortured by you. In a good sense, of course. Anyways, thank you so much, and enjoy the rest of your day, and I will see you again on Friday. Thank you.
Professor, this is